Welcome back. Today we're going to talk about systems of equations. So the first thing I want to do is I just want to review how to graph a line. Okay, so remember that when we have a line like y is equal to 2x plus 1, if we were to graph this line, remember that this is the y-intercept. So the first thing I do is I plot the y-intercept. And this right here, if I make it into a ratio, it's the slope. So I go from the y-intercept, I go up 1, 2, and over 1. Remember that 2 over 1 is the same thing as negative 2 over negative 1. So I can also drop down 1, 2, and left 1. I can also go down 1, 2, 3, 4, and over 1, 2. That's equivalent. Or let's get a couple more points here. Okay, so here I've plotted the line, and I always draw the line as long as I am able to, given the constraints of the graph here, and I always put arrowheads on it. Okay, and one more thing I want to note is if you have an equation that's in standard form, like x plus y equals 3, for instance, what you can do is, let's actually make this a little bit better, like 3x plus y is equal to 3. The way you can graph it is you can graph it using the intercepts. So let's go ahead and try that here. So let me get rid of this line right here real quick so that we can do that. All right, so when you're graphing something like this, you can think of putting, if I put 0 in for y, what I would have as an equation is 3x is equal to 3, and if I solve this, I get x is 1. So that's the y-intercept because it's the value, sorry, that's the x-intercept because it's the value when y is equal to 0. It's the x value when y is equal to 0. One quick way of doing that is if you have this on your paper, all you do is you put your finger over the y term to get what the x term is. Okay, and likewise, if you have 3x plus y equals 3 and you're trying to get the y-intercept, put your finger over the x term and come up with your equation y is equal to 3, and that is right there. That's your intercept. So 1, 2, 3. Okay, so you have 2 points in the line, so you can go ahead and graph it. I'm just going to move this around to be part of this point, these points right here. Works out pretty nicely. So here's my line right here that goes to those 2 points, and I can put arrowheads on it. Okay, what I want you to remember is that every point on the line is a solution to the equation. And so if I take a point like this one, which is, it should be 0, 3, I can put it into this equation. 3 times 0 plus 3 is equal to 3, and it would be a solution. So it would result in a true statement, which in this case would be that 3 is equal to 3. Okay. All right, when you have a system of linear equations, what you're doing is you have 2 or more equations that have the same variables in it. So that's called a system. It's a set of equations that have the same variable. An ordered pair is a solution, like a single ordered pair is a solution to a system if it is a solution to every equation in the set. So we're gonna talk about 3 different techniques in order to solve systems of equations. And the first one we're going to talk about is how to solve them using graphing. So the first thing I want to do is I want to find the set of solutions that represent the solutions to this equation. And how do I do that? Well, I just graph it, right? So here I have a y-intercept of 2 and a slope of 3. So I got 1, 2, 3, and over 1. 1, 2, 3, over 1. Okay. And I'm going to carefully plot my points right here and extend my line a little bit. Okay. And I put arrowheads on it. So I've plotted the first one. Okay, and then I'm going to plot the second one. So it's a y-intercept of positive 3 and a slope of down 2 over 1, down 2 over 1. Okay, and what you may have noticed already is that these 2 lines actually intersect. Okay, and so what's so nice about this right here is that the 2 lines intersecting means that, so let me just, they intersect right here, and that point is 1, 1. Okay, and so 2 lines intersecting here means that both of the, it means it's a point of intersection on 2 lines means it's a member of both of the lines. So what does that mean? Well, geometrically, it's a point on both the lines, but algebraically, every point on the lines are solutions. So that means that this point is a solution to the first one, and it's also a solution to the second one. So here, what I do is I can check this by putting 1, 1 into both of these. So 3 times 1, oops. So let me check it down here. 1 is equal to 3 times 1 minus 2. 1 is equal to 1, that's true. 1 is equal to negative 2 times 1 plus 3. 1 is equal to negative 2 plus 3, which is true. Okay, so it's actually a solution to both of them. I checked it. So I would consider 1, 1 to be the solution to the system of equations because it's the solution to not just one equation, but both of them simultaneously. Okay, so what is a solution to a system? When we say we solve a system of simultaneous equations, which is also a system of linear equations, they're just we sometimes call them simultaneous equations. What we're looking for is a point or points that are solutions to both equations. And oftentimes geometrically, what that looks like is it's the point of intersection of the two lines. Now, as you may have noticed already, sometimes lines meet, like lines that are parallel always meet at a point, but sometimes lines don't meet, and sometimes they're just parallel. And remember that if you have parallel lines, what you notice is that they have the same slope, but they have different y-intercepts, okay? And every once in a while you come across a situation where the two lines are actually identical. Like for instance, if I have y is equal to 3x plus 4, well, this is going to be the same thing as 2y is equal to 6x plus 8. All I did was I took this top one and I multiplied it by 2. So if these two equations were my system, then what's going to happen is they would be the exact same line. Okay, well, here's the classification. If you have two lines and they meet at one point, this is called, there's exactly one solution, right? It's this one. It's the ordered pair that whatever this A comma B is. And this is called a consistent and independent system, right? The system itself, the two equations taken together is called a consistent and independent system. Okay, if what you definitely know about them is they have different slopes, all right? Because if they have different slopes, it means they're not parallel. If they're not parallel, that means they'll intersect exactly once. All right. Now, if you have two equations that end up being the exact same equation, what that means is that it's a consistent, meaning consistent means it has at least one solution, and dependent meaning the solutions to one depend on the other. Another way of saying this is that there are an infinite number of solutions. Every single point on the one line is going to be a point on the other line. So every single point along here that's a solution to one equation is also going to be a solution to the other one. So the system itself, the two equations taken together that make it a system, has infinitely many solutions. All right. What do the equations look like? Well, they have the same slope and they have the same y-intercept. Now, an inconsistent system is one where there's no solutions, and that's because you have parallel lines. That looks like it has the same slope, but it has different y-intercepts. All right. So there's absolutely no point of contact between these two lines because they're parallel. And so the system has no solutions. Remember, we don't say the solution is 0, 0. Sometimes students confuse the origin with an identification of no solutions, and that is simply not true. Those lines do not meet at the origin. They just never meet. Okay? Let's go over one where you have to graph it in with intercepts. So remember, to get the x-intercept, I cover it up. So I get 2x is equal to 4, so x must be 2. Okay? For the next one, I cover this one up. So I have 2y is equal to 4, so y must be equal to 2. So there's the first one. Once it goes through two of them, I'm going to extend it here. Okay, now for the second one, we have both x and y have a y-intercept. X is equal to 2 is a y-intercept right here, and y is equal to 2 is a y-intercept. So here, we actually have two equations. We have the same equation right here. So this is in a consistent, dependent. And there's an infinitely many solutions. And the reason why this is the case is, if you notice, if we go back to the original two problems, is the first one is a multiple of the second one, meaning if I multiply the second one by 2, I would have 2x plus 2y equals 4. Okay? Okay, so this is a word problem we're going to tackle today. Keisha and her friends visit the concession stand at a football game. The stand charges $2 for a hot dog and $1 for a drink. The friends buy a total of 8 items for $11. And we want to know how many hot dogs and how many drinks they bought. Now, the thing about writing a system of equations with these word problems is that it's a system, right? So we're looking for at least 2 equations, and in 8th grade we're just going to deal with 2 equations. So I'm looking for 2 equations basically, and so from this description I've got to figure out what my 2 equations are. Okay, so usually in this, x and y are, so first of all, there's going to be 2 variables. X is going to represent something and y is going to represent something. So there's going to be 2 variables and there's going to be 2 equations. All right. So we've got to determine what x is going to be equal to, right? So and usually in these problems, x is going to be equal to a number of something and y is going to be equal to another number of something different. So here, we're going to let x equal to the amount of hot dogs that we have here, okay? And we're going to let y equal to the amount of drinks. Now, the reason I knew I had to set x and y equal to what I did was because there's information about how many items that they bought, okay? So that's literally like altogether, if you bought a hot dog, that's considered 1 item. If you bought a hot dog and a drink, that's considered 2 items. So they gave us this weird information that there's going to be 8 items sold totally, and that the price of them is going to be $11. So we have information about the cost and we have information about the number of items. Okay, so let's think about this for a minute. It's $2 for a hot dog and $1 for a drink. Okay, actually, let me take a step back. The idea that there are 8 items total means that if I take the number of hot dogs and I add it to the amount of drinks, I get 8. That's the first equation I have. So the total amount of items is just going to be x plus y equals 8. Okay. The second thing that we know is that it's $2 a hot dog and $1 for a drink. So so the total amount here that I spent, or that Keisha and her friend spent, is $2 times the amount of hot dogs they bought, plus $1 for the amount of drinks they bought, and that totaled up to $11. So one equation is going to be the number of items, while the other equation is going to represent cost. So I use the information about cost to get one equation, and I use the information about number of items to get the second one, because really I'm looking for a system of equations. Now when you have this, remember the first thing you want to do to graph it is you want to solve it for y. So this x plus y is equal to 8. I want to subtract x from both sides. So what I would get is y is equal to, and I want to write it as negative x plus 8. Let me go ahead and graph that. So 8's here. Negative x means it's negative 1 over 1. So I want to drop down by 1 and over by 1. So here is my first equation. When I graph it, gets this, right? So here's my first equation. And I'm actually not going to put arrowheads on it because my x's and y's can't be negative in this situation because it's hot dogs and drinks and they don't need to go negative, right? So there's no arrowheads. They just stop at both the x and y intercepts. So if I buy 8 hot dogs, I would buy 0. Well, this would represent 8 hot dogs and 0 drinks, but I'm not even sure if I can do that because they don't have enough money to do that. So let's look at the second equation. So we have 2x plus 1y is equal to 11. Well, that's just, let me go ahead and write it down here. 2x plus y is equal to 11 because I don't have to put that 1 there. So I'm going to write this like this. So I have y is equal to negative 2x plus 11. Well, if I graph that, this would be 11, and negative 2x means I go down 2, 1, 2, and over 1, down 1, 2, and over 1, down 1, 2, and over 1, down 1, 2, and over 1. So here's this is my second equation here. Now, and again, I don't want to ever have a negative because my cost can't be negative. Yeah, my cost can't be negative. So here, what I'm looking for is the intersection of these two equations, because that's going to be the amount of x and y's that's the x and y coordinate that satisfies both of them. Notice that because of the way this works, I actually have to satisfy both inequalities, equations in order to answer this question, right? So both the total of their items has to be 8, and they also can only spend $8. Now, the first line represented every amount of hot dog and drink combinations where the hot dogs plus the drinks equal 8, right? But the second equation is everything hot dog and drink combinations that total up to $11. So the intersection represents both the situation where both of the equations are satisfied. So at 3, 5, when they buy 3 hot dogs and 5 drinks, let's check this out. Let's check our solution here. 3 hot dogs. So if the hot dogs are $2 each, so it's 2 times 3 plus, and the drinks are $1 each, but 1 times 5, that should be equal to 11. So that's 6 plus 5 is equal to 11. So the coordinate 3, 5 really means, and this goes to interpreting solutions, they bought 3 hot dogs and 5 drinks. Because that combination is the only thing that satisfies both of the parameters here, that the total number of items adds up to 8 and they spent $11. So that's how you can build a system of equations based on a word problem. Notice that I had to do 2 different things, 2 different equations. One was the total number of items and one was the cost of all the items. I graphed them, I found their intersection, and then I went back and I interpreted the intersection, the XY coordinates, to the word problem, right? So now I'm looking at hot dogs and drinks, and so my interpretation is really important, because the hardest part is like looking back at your answer and thinking about what this means in terms of the word problem. All right, so this is how you can build and solve a system of linear equations based on a word problem. And that's the end of the lesson for today.